In this module, we're going to discuss the so-called forward equations. The forward equations enable us to compute the prices of what are called elementary securities. An elementary security is a security that pays $1 at a particular time and in a particular state at that time. We'll see that by constructing the forward prices, we'll be able to price many derivative securities very easily. So let's get started. We're going to let P subscript I comma j superscript e denote the time zero price of a security that pays $1 at time I in state j and 0 at every other time and state. Such a security is called an elementary security. Actually, it is sometimes also referred to as an Arrow-Debreu security for those of you who have some background in economics. This type of security actually has a very important role to play in financial economics. So such a security is called an elementary security, and we call P subscript I comma j superscript e its state price. We can actually see that these elementary security prices satisfy the forward equations. So these are the forward equations. We'll explain where they come from in a moment. We note that P00 superscript e equals 1. Why is this? Well, this quantity here is the time zero value of $1 that is paid at time 0 and state 0, i.e. today. So $1 today is equal to $1 today. So certainly this is true. So starting with this value, we can actually work forward in time to compute the values of the Pij's at every node. For example, suppose this is our binomial lattice. Well, we start off with knowing this value, it is 1. And now we can use the forward equations to get the values at these t nodes. So this value here, 1, is equal to P00. I'll ignore the superscript e just to avoid cluttering the slide. This value we want here is P10, and the value we want up here is P11. Well, if you look at these, we can see how to get them. So we can get P10 from this equation, and we can get P11 from this equation. In this case, we would take k equal to 0, and in this case, we would take k equal to 0, and that's how, we would take, k equal to 0, and that is how we can calculate the state prices at time 1. Given that we now know these three state prices, we can go forward to calculate P21, or rather P20, P21, P22, again using these two equations for the P22 and P20, and we can use this equation here for P21. So actually, this is why they're called the forward equations. We start off with P00 equal to 1, and we actually use these equations to work forwards in the binomial lattice to calculate the state prices for every node. So where do these forward equations come from? We're going to answer that question on this slide and hopefully make clear where these equations come from. So for example, let's consider this elementary security. This is the elementary security that pays $1 at time t equals 3 and state 2 and 0 everywhere else. So by definition, the value of the security is P3, 2. However, we can also compute the value of the security another way. We can just treat this as a regular security and use risk-neutral pricing to compute its value. So if we use risk-neutral pricing, we will work backwards in the lattice in the usual way to find its value. So let's do that. So if we work backwards, we can come back to this node. This is node R22 up here. Well, the value at node R22 is going to be 1 over 1 plus R22 times the expected value of the security 1 period ahead. Well, 1 period ahead, the value of the security is either 0 or it's 1, and so we get this quantity here, which simplifies down to this expression here. So this is the value of this elementary security at time t equals 2 and state 2. Its value at node n20 is clearly 0 because at time t equals 2 and state 0, you'll only get 0 in the two successive states, so its expected discounted value must be 0. So therefore we have this. Its node at n21, which is here, Well, that is given to us by 1 over 1 plus R21 times the expected value of the security 1 period ahead, and that is 1 with probability a half and 0 with probability a half. And so we get this quantity over here. So what we've done is the following. We've come to this elementary security, which is worth 1 in this state and 0 everywhere else. We know by definition the value of this elementary security is P32. But by working backwards in the lattice, we've also computed its value at these 3 nodes. It's equal to this at R22. It is equal to this at R21. And it is equal to 0 at R20. So therefore, we can say that P32 over here must be equal to this quantity times the value of $1 at that node. Well, the value of $1 at that node is P22, plus this quantity times the value of $1 at this node, and $1 at that node is actually P21, plus $0 times the value of P20, which is the value of $1 at that node. So in fact, all we're doing here is linear pricing. We're actually breaking this security up into this many units of P22 plus this many units of P21 plus 0 units of P20. And so we get this equation here, and this is indeed, in this case, equation 13. So this is equation 13. So this is the argument that you get to show that the forward equations are true. It's easy to see that this holds in general for any node, any time k, state s. If we're at an extreme node at the bottom or at the top, well, there's only one predecessor node that's possible, and so we would only get one term in this equation, and that's why we would get either this equation here or this equation here. So these are the forward equations. We can calculate the state prices or the elementary prices by working forwards in time from t equal to 0. So let's go back to our familiar short rate lattice. This is the short rate lattice we're considering throughout these modules. We start off with R equal to 6%. It grows by a factor of U equals 1.25 or falls by a factor of D equals 0.9 in every period. So we're going to actually compute the forward prices in this particular model by starting with P00 equals $1 and working forwards to calculate the forward prices at all future nodes. And this is the lattice with the corresponding elementary prices or state prices. So the value at any node Nij is actually Pij, the value of the elementary security that pays $1 time I state j. So how do we get these values? Well, we know where the 1 comes from. We can work forwards using the forward equations to get these values. So for example, how do we get this value of 0.3079? Well, we know from the calculation we just did in the previous slide that 0.3079 is going to be equal to 0.2194 divided by twice 1 plus the short rate prevailing at this node plus 0.4432 divided by twice 1 plus the short rate prevailing at that node. So this is just the same calculation that we did in the previous slide. We find that 0.3079 is equal to the sum of these two quantities here. Now what can you do with these elementary prices or these state prices? Well, once you've calculated these state prices, many other derivative securities are very easy to calculate. For example, suppose we want to compute Z04, the price of the zero coupon bond. So this is the zero coupon bond, its value at time 0, maturity 4. Well, with face value 100, we can compute Z04 as just being 100 times the state prices, the sum of the state prices in all of the states at time t equals 4. So what are those states at time t equals 4? Well, it is these quantities here. So remember, a zero coupon bond is going to pay $100 at this node, $100 here, $100 here, and so on. So how much is that worth? Well, that must be worth 100 times this elementary security price, plus 100 times the elementary security price for this node, plus 100 times the elementary security price for this node, and so on. Again, that is just linear pricing in action, and so that's how we get Z04 equals 100 times the sum of these elementary security prices, 0.0449 and so on, and actually that sums to 77.22, which we have seen before. We saw this in one of the first modules in this section where we computed zero coupon bond prices by working backwards in the lattice. Well, we've done it in a different manner here. We've done it here by first calculating the forward prices by working forwards in time and iterating those forward equations, and then given all of the elementary prices, it was absolutely trivial to compute the price of a zero coupon bond. It was simply the face value times the sum of all the elementary prices at that time. We can also calculate other security prices using these elementary prices. So here's another example. Consider a forward starting swap that begins at t equals 1 and ends at t equals to 3. The notional principal is $1 million. The fixed rate in the swap is 7%, and the payments are received at time t equals I for I equals 2 and 3. So this is where the forward feature kicks in. If it was a regular swap, you would get a payment at time t equals 1. Here we're assuming that you only get a payment at time t equals 2 and time t equals 3. And that payment is based as usual on the fixed rate minus the floating rate that prevailed at time t equals I minus 1. So the first payment is at t equals 2, because payments are made in arrears. So the question is, what is the value V0 of this forward swap today at time t equal to 0? Well, how can we calculate that? Well, actually, it's very straightforward. So what we have here are the actual cash flows for the swap. There are actually 5 cash flows, and we can go back to see these cash flows by looking at the short rate lattice. So these cash flows are based on these short rates. They occur in arrears. So we should be seeing these cash flows of 7.5 minus the fixed rate of 7%, 5.4 minus 7%, 9.38 minus 7%, and so on. These are the cash flows of the underlying swap. And so indeed, here they are. These are the fixed rate of 7% minus the floating rate 9.38, 7.5, 5.4, 6.75, and 4.86%. So they're the cash flows of the swap. But remember, these cash flows are paid in arrears, one payment ahead. So what we do is we take these cash flows and discount them by the appropriate short rate. So it's 9.38%, the same value as in here, 7.5%, same value as here, and so on. So now we've got the value of the cash flows at each of the nodes at which these cash flows are determined. Given that we know the elementary security prices for those nodes, it is just a simple matter of multiplying these values by the corresponding elementary security prices. And that is exactly what we have done here. So we see we get a value of $5,800 for a notional principal of $1 million. So again, we could have priced this forward starting swap if we liked by working backwards in the lattice using risk neutral pricing. Well, instead we've done something differently. We're still using risk neutral pricing, of course, because that's where the forward equations come from. But what we've done instead is we've determined the elementary security prices via the forward equations and then used those elementary security prices to compute the fair value or the arbitrage-free value of the cash flows associated with this forward starting swap. All of these calculations, or certainly the calculations for the elementary security price, are available to us in the spreadsheet. So we have our short rate lattice. You can see how we actually calculate the elementary prices. We start off with a value of 1. And then we just iterate the forward equations. So we get 0.4717, 0.4717 in these two nodes at time t equals 1. And we can actually iterate forward the forward equations. We're using if statements in here to make sure that we're actually using the correct version of the forward equations. There were 3 different versions that we saw. We need to make sure that we're using the correct one. And so that's how we do that. We just copy and drag these formulas through the lattice and obtain the elementary prices at each node or each cell in the lattice. Given these, we can actually now compute all of the zero coupon bond prices. Calculating a zero coupon bond price is now absolutely trivial. We just sum the corresponding elementary prices, multiply them by 100, and that's how we get the zero coupon bond prices. So down here you can just see we're just summing the corresponding elementary prices, multiplying by 100. And then of course we can invert the zero coupon bond prices to get the spot interest rates for that maturity. So for example 6.68% we get by inverting the 77.22, assuming per period compounding. And we did that calculation as well in an earlier module.